Hope all of us are doing fine. My name is Ernest, and this is our Ernest Sciences and Mathematics TV channel. I'd like to welcome all our members into the discussion for today, and I kindly request us to subscribe, engage us in the comment section, and also ring that notification bell to be getting updates on our various uploads in mathematics and sciences. So in our discussion today, I'm going to look at the translation motion of rigid bodies. And this is going to be an extension of our previous discussion, which we have done basically on the concept of the degrees of freedom, whereby I said that basically for rigid bodies, they're going to be having 6 degrees of freedom, which of course we said which constitute the 3 for translation and of course 3 for rotation in that specific case. Now in this particular discussion, we're going to look at the concept of translation, and of course that's going to be involving the Cartesian coordinate system, which we said of course is going to be giving a set of the first 3 types of translation along the x, y, and z axis given as such. So in this case, we're going to consider 2 Cartesian coordinate system for x and y, and of course the illustration on our right side of the board is going to be giving us basically what we refer to as a rigid body. So in this case, this is going to be this specific body, and we're going to consider 2 points on that rigid body given as A and B. And in this case, for us to describe the aspect of motion, we are going to consider its relative position vectors given in terms of r. And of course, we are going to consider the absolute position vectors given in terms of r. And we are going to, so this is going to be position vectors, absolute position vectors given in terms of r. And then we are going to consider the velocity component, which we are going to look at, especially with respect to this point which we have given on the board. And lastly, we shall look at the acceleration component, which are going to assist us in trying to describe this specific translation motion of such a kind of rigid body. Now, using the concept of vectors, we are going to get a position of either A and B relative to one another. And in this case, we can describe the relative position or the absolute position vector of RB given in terms from vectors. This is going to be given in terms of the summation of A and this specific component of this position, absolute position component of RB over A, and this is going to be giving the position between A and B given as such. So therefore, we are going to have this one given in terms of the summation over A and RB over A given as that one, forming our what we call our of course absolute position vectors, giving us as one in form of another one given as that one. So in this case, if we consider a fixed coordinate system given in terms of this x and y with the origin, now these position vectors can be described in forms of a velocity component, and therefore we're going to consider this particular case whereby we're going to describe a velocity of this particular system. Now, in case if we are required to find perhaps the velocity of a particle at B, in this particular case, we can give it in terms of the velocity at B is the sum of the velocity at A. So using vectors, still we can describe this one with respect to the position vectors which we have given as such, and this is going to be given as this one. So if you try to look at this specific description, we can as well have an extension of this particular representation given in terms of a V sub A plus. So from a description of motion in our various videos, we have said that if we take the first derivative with respect to time of this position vector of a BA, we're going to see that since this one is going to be given for these 2 points which are constant on the rigid body. Now in our previous discussion, I said on this specific point that the 2 points on a rigid body, whenever this body undergoes motion, are going to maintain their distance. So in this case, we're going to expect RB over A to be a constant one, and therefore the derivative with respect to time of this specific position vector is going to be giving us 0. So this one will have an implication of VB equivalent to VA, and therefore giving an impression that the velocity components or all the particles, if we consider A to be a particle and B to be a particle, and then therefore all the particles in a rigid body are going to be moving with the same velocity component as we have given. So this will have the same implication for acceleration. Now, in this case, if we had an acceleration of this specific particle at A, at B, then therefore we're going to give this one as a derivative of the first one, which is going to be a acceleration of the particle at A plus acceleration of the particle at this specific position over A or B over A. So in this case, we're going to see that, as we said, the distance between the particles during motion of a rigid body are going to be the same. So we are going to expect the second derivative with respect to time on this specific component of the velocity of RP over A still to be equivalent to 0. So that one implies, this is going to be acceleration. That one implies that basically the acceleration over A sub P is equivalent to A sub A given as that one. And therefore, from these two specific equations, we're going to see that the velocity component and the velocity component and the acceleration for a rigid body are going to be the same. And these are going to be true for what we refer to as a translation type of motion. So in case we come across them, we're going to be treating them as such. And that's going to be giving us a clue on how we can describe a translation motion of what we refer to as rigid bodies. Now, last but not least, I'm going to look at an aspect of angular displacement, which basically is not going to be form of this, but it's going to assist us contrast this specific discussion we have had with the concept of translation motion. Now, if this particular body is going to move along a circular path, we are going to describe the angular position given in terms of theta. Now, if we have angular displacement or the change of this specific position with respect to time, then therefore we're going to have a d theta over dt, which is going to be a change in angular position. And this is going to be giving us what we refer to as angular displacement. Now, if we consider angular displacement with respect to time, and therefore that's going to be giving us what we refer to as angular velocity. And this angular velocity is going to be given in terms of omega. Now, therefore, we can describe this specific aspect of omega by having the first derivative of this specific displacement with respect to time. And in this respect as well, we can as well evaluate what we refer to as the angular acceleration given in terms of the first derivative with respect to time of this angular, of course, velocity given as that one. And this is going to be giving us alpha, which we can give in terms of angular acceleration. So in a summary form, that's how we can depict the concept of a circular motion of a body in terms of a position, of course, which is going to be given in terms of angular position. And from this angular position, the change in angular position with respect to time is going to be given as angular velocity given in terms of omega. And lastly, we can give the angular displacement or angular velocity with respect to time in terms of alpha, which is going to be angular acceleration. Now, we shall mention this one in a subsequent video, which is going to assist us, of course, try to describe other forms of motion of rigid bodies apart from this concept of translation. Now, we shall have a range of course, videos which we are going to do in terms of evaluations. And kindly check out description boxes for various links of other videos. Subscribe and engage us in the comment section to be having an update on such a type of content which we are going to do later, or the ones which you have already done. So that is it for now, guys. Bye, God bless you. Catch us in our next video.